All right, so today we'll finish up with the last two transformations we haven't done. That's the amplitude change and the period change. Both of these transformations are non-rigid, okay, which means it's actually going to take the sine or cosine wave and distort it. All right, so up until now, the height of every sine or cosine wave that we've studied has been what? What's the height of every wave? It's always been 1. Even if you shift it up 6 units, the height is still 1. Okay, the height is the distance measured from that center line, going right through the function. And the distance you go from the center line up should be symmetric with the center line down. Okay? Now, since we're measuring a height, okay, amplitude is a height, what kind of number do you think amplitude always has to be? It always has to be a positive number. So if you're describing the amplitude of a function, you should never give me a negative number. Okay, and I mentioned that in the next slide. Okay, so an amplitude change has the form c times sine x or cosine x. And again, the reason I'm using the letter C is because once we learn all 4 transformations, and you have to do them in a certain order, this would be the third one that you do. Okay, so if all you want to know is the amplitude, okay, of your function, you just take the absolute value of the number in front. So again, that means it would always be positive. That's why we take the absolute value. All right, so let's scroll down. I just want to see if I have some examples. Yes, I do. Okay, so we'll look at some examples after about calculating amplitude. So if there's a negative in front, right, we'll talk about what that negative does. It doesn't have an effect on the amplitude, but it does have an effect on the graph. Okay, so when we get to describing the amplitude and graphing, I'll talk more about that. Okay, but any questions on how to find the amplitude of a function? Just take the absolute value of the number in front. Or if there's no number in front, like if we just had this, you could always put a 1 in front. Okay? So that's why the amplitude of every function we've studied so far has been 1. There hasn't been any number in front. Right, so an amplitude change will stretch or compress your graph along the y-axis. Okay, so that means the y values are going to change. And does anybody know how we would perceive that as a sound? Yeah?
Could it get louder or quieter if we stretched or compressed it?
Yeah. So if I just put this at, play a frequency of like 950 hertz. So if I play it like this, okay, you can hear that. And then if I drag it to the right, I've just done a vertical stretch. And now it's louder. Right, so that's the effect of vertically stretching and compressing. It gets louder or softer. So let's look at a few problems, and you'll have some just like this on the test, where you don't have to graph it. All I want to know is the amplitude. I just want the amplitude of this function. Okay, so what's the amplitude of that function? 3. Now, is that different than the range of the function? Yes. How would you describe the range of this function? Ellie? Yeah, this one, the range would be -3 to 3. So the range is an interval. Okay, it's a lowest to a highest value. The amplitude is just a single number. Okay? Now, if the number in front is a 3 or a 4, like if it was a 4, the amplitude would be 4, and the range would be -4 to 4. Is that range always going to be the same as that number? Like if it's a 5, would it be negative, not 5 to 5? Like, can anybody think of an example when the numbers that describe the range are different than the number that describes the amplitude? Yep. Yeah, if you do a vertical shift, okay? Because now you've shifted up, so the range numbers might not be the same as the amplitude numbers. But that's getting into multiple transformations in the same problem. But if you get that idea, that's pretty good. Okay, what's the amplitude here? 4/3. Yep. What does the pi over 2 do? That's a phase shift, shifting to the left. And what about the +6? That shifts it up 6. Those two numbers have no effect on the amplitude. Okay, so you got to know what number you're trying to focus on. You're looking at that 4/3. Okay. What if I went like this? The amplitude is still 4/3. That negative just changed the graph, though. Okay, it did something to it, but it didn't change the amplitude. Okay, how about negative 2 sine x? 2. Okay. So any questions on finding the amplitude? Okay. Anybody think they know what this, what the negative does to the graph? Like if you were to graph 2 sine x versus negative 2 sine x. They have the same amplitude, they have the same range, but they're not the same graph. Josh?
Will they be inverses? So when 2 sine x is going up, 2 sine x is going down, or something?
Yeah, they're going to be reflections of each other. Okay, they'll be mirror imaged. Okay, over either the x or the y-axis. In this case, if you put it in front, that would be a vertical reflection, so it would be mirror imaged over the x-axis, over the x. All right, so just like with the phase shift and the vertical shift, we have to figure out where those 5 original points are going to go. Well, first of all, since we're stretching up and down, the x's stay the same. So copy down all your original x's from the table. Okay, and now to find the new y values. When we did a vertical shift, all we did was add or subtract the shift to all the y values. Anybody think they know what we're going to do this time to the y values? What? Yeah, we're going to multiply all the old y values by c. Okay, notice here that it says c. It doesn't say absolute value of c. Okay? Whatever number is in front, that's what you would multiply by. Okay? So I'm going to skip ahead. I can come back to this in a second. But in this problem, I would multiply the y values by 3. I'd multiply the y values by 1/2. How about in that problem? I'd multiply the y values by -1. Okay. So we'll go through each of those problems, but that's basically all you do. The only time you take the absolute value of c is if I ask you the question, what is the amplitude? You should never give me a negative number for that. Okay, and just a reminder, like every table we've made, no decimals in the table. Okay, everything should have pi or multiples of pi. Okay, does everybody have the 2 steps? All right. Okay, so let's try to graph 3 cosine x. All right, so now we know 3 transformations. Okay, we know the phase shift, we know the vertical shift, we know the amplitude, or vertical stretch, change the amplitude. Now we got to figure out which one of the 3 it is. Okay, this one is an amplitude change, or vertical stretch, but can anybody tell me how I know that? What about the 3? How do I, yeah. It's in front of the cosine? Okay. Can we be even more specific? Because I could put it after the cosine and still make it a vertical stretch. This would look kind of weird, but I could do this. That's the same problem. Still tripling the cosine. Yeah?
You're multiplying 3 by the cosine.
Right, that's the key. You're multiplying the cosine function by 3. Okay? I don't know if we mentioned it yesterday, but you could do the same thing with a vertical shift. A lot of times we put the +2 at the end, but you could do it in the beginning, and that's still a shift up 2. Okay? So keep stuff like that in mind. All right, so since it's a vertical stretch, what values are going to stay the same? Going to keep the x's the same. Okay, just like I keep saying, 1 point for each x and y value in the table. Okay, so Andrew, what would be my original y values for cosine? So 0, 1, 0, negative 1, 0. Does everyone agree?
1, 0, negative 1, 0, 1.
Yes. 1, 0, negative 1, 0, 1. Okay, so those would be the originals. And Quinn, what am I going to do to all those y values? Yeah, just got to multiply them all by 3. Okay, so Trevor, can you tell me my final y values?
3, 0, negative 3, 0, 3.
Now, when we draw it, this could look very similar to the original, depending on how you scale your axes. Mine's going to look identical to the original, because I'm going to go like this. I normally label those as 1 and negative 1. I'm going to do them as 3 and negative 3. You don't have to if you really want to do something like this and fill in all the marks. You could do it that way too. But I think it's just as easy to go like that. All right, so now I've got pi over 2, pi, 3 pi over 2, 2 pi. All right, so 3, 0, negative 3, 0, 3. And there's our graph. Okay, any questions on that? The reason I like to do it this way is because now if you ask me to graph 6 cosine x, I could do that very easily. There you go. Okay, there's your graph of 6 cosine x. It looks exactly the same because I changed the scale on my axes. So if you do it that way in your homework, which it's fine to do it that way, you're just going to notice, hey, all my graphs look the same, okay? Because you're changing the scale. Questions on that idea? Yeah?
Would it only work that way for those 3?
No, if you wanted, like, for me to graph 5 cosine x, I could just make this a 5 and make this a negative 5. And now that's a graph of 5 cosine x. Yeah, basically any number you want. I could just change my y max and my y min, and there's your graph. Okay, any other questions on that? If you don't want to do it that way and you really want to see how all the graphs are different, then you need to keep your y scale the same on every single problem, which can be kind of hard if you've got problems where you have to go as high as 10, and sometimes you only have to go as high as 2. And it's going to be hard to keep your y scale the same. Like this one, you only have to go as high as a 0.5. So if I was trying to graph this one on those axes, I would only be going to like right there and right there. My graph is going to look so squished, it's going to be really hard to even tell that it's a wave. And I think we've seen that on the calculator sometimes. If you set the wrong window, you can make a wave almost just look like a line. So you got to I always start with zoom 7, which is zoom trig. Okay? We use zoom 6 a lot in algebra. With trig, we do zoom 7. All right, so let's do this one. Okay, same format as the last one. You're multiplying by a number in front. Okay, so that's your vertical stretch. Well, actually, it's an amplitude change. Can anybody tell me, is it going to stretch or compress? Yeah. It's going to compress vertically. Okay, so this would be like a softer acquired sound. What's nice about the vertical stretch and the vertical shift is they do exactly what you would expect. Put a big number in front, it stretches the graph bigger. Put a fraction smaller than 1 in front, it compresses the graph smaller. Okay. Vertical transformations do exactly what you would expect. Horizontal transformations do the opposite. Okay, so you need to remember that for the test. Horizontal does the opposite. Vertical does what you would expect. All right, so fill in your x values. And now we're going to take all the original y values and multiply them by a half. Anyone think they can tell me the final answers without me writing the original y values?
0,
Mm-hmm.
1/2, 0, -1, 0.
Yep. And now again, depending on how I set up my scale, this could look just like the regular sine function. Okay, I'm going to make each tick mark a half and negative a half. So I'm going by 0.5s on my y-axis. And now your x-axis, we just label exactly the same for every problem in this section for this type. Okay. The next type, we will not be doing the x-axis the same. All right, so we've got 0, 1, 0, -1, back to 0. Are there any points of inflection on that graph? Pretend that it, if it kept going, out of the 5 points that I drew, are any of them points of inflection? Yep. The first, the third? Yeah, the first, third, and fifth, those are all points of inflection. Between the first and the third, you're concave down. Between the third and the fifth, you're concave up. And then after the fifth point, it's going to switch back to concave down. And before the first point, it's going to switch back to concave up. Okay, so there's three points of inflection there. And a lot of times when you're graphing trig functions, if you don't shift them up and down, the points of inflection are also x-intercepts. But that doesn't have to be true. Now I still have 3 points of inflection on that graph, but none of them are x-intercepts. So don't think that a point of inflection is always on the x-axis. It can be up or down or anywhere else. Good. Any questions on that? All right, and the last one, I would almost argue that it's not an amplitude change, but it kind of follows the same pattern of how you would solve it. Why could you argue that this one isn't really an amplitude change? Yeah, the amplitude is still 1. You're not vertically stretching or compressing it here. Okay, what are you doing? Yeah, you're just flipping it. Okay? You're flipping it over the y-axis. So what ends up happening is you're just going to multiply all your y values by what number? Yeah, by -1. All right, so normally we would have 1, 0, -1, 0, 1. Change the sign of all those numbers. -1, 0, 1, 0, -1. Any questions on that? All right, so let's graph that. Got 1, -1, pi over 2, pi, 3 pi over 2, 2 pi. Okay, so we're starting at -1, 0, 1, 0, -1. And keep going. All right. Anybody think of another way I could get a picture that looks like that without doing a negative in front of cosine? I want to stick with the cosine function though. Anybody think of another way you could get a graph identical to that? Yeah, Allie?
Can you just shift it and then extend the graphs like this?
So how much would you have to shift it by to get that graph? Sticking with cosine.
You have to shift it pi and pi
Yeah, you have to shift it by pi. So pi to the which way?
plus pi to the left.
Could you shift it pi to the left? Yeah, I think you would have to shift it to the right by pi. So if we were to graph let's graph what I have, negative cosine x. And then I graph cosine x, and we're going to shift pi to the right. So would that be minus pi or plus pi? Minus pi. Okay, and I'm in radians, so that's fine. Let's graph those and see what happens. They're the same graph. Well, at least they look like the same graph, and they are. Okay, we could prove algebraically that they are the same. The graph suggests that they're the same. All right, so the point here is there's many, many ways you can get the same picture. If I just showed you that picture and said, tell me the equation of that graph. Well, there's two ways you could do it. You could even do it a third way. How could I do it with sine somehow? Anybody think how you could use the sine function and get that same picture? Yep.
Sine of x minus pi over 2.
Yeah, if you take sine and shift it, all right, let's type back in what I had. What else do we have? Cosine of x, was it minus pi? All right. And then, Allie, can you tell me what you said again?
Sine of x minus pi over 2.
Minus pi over 2. So let's graph those and see what we get. I didn't do zoom 7, which is why it looks a little squished, but it's okay. So there's the two we had, and there's sine. So there's a third way to get the same picture. Okay, so all kinds of different ways to get the same thing. Any questions on that? All right. So let's take a look at the last transformation, which is a period change. So period changes, I think, are the most interesting from kind of a demonstration standpoint, because you can do all kinds of different things with different frequency sounds. So remember, the standard period, okay, the amount of time it takes for a function to go through all its values before it's going to repeat, is 2 pi radians. Okay, that's if you don't do anything to it. And that's the period of every single problem you've had in the notes and in the homework this week up until right now. You've had to go through 360 degrees before the function repeats itself. Okay, so a period change has the form y equals sine bx or cosine bx. So you're multiplying again, just like you did with a vertical stretch. But what's the difference with this multiplication? versus when we just did it in the last type of problems? Right, it's inside the parentheses. Okay, that's the big difference. You're multiplying the x inside the argument. Okay? Now, I said that there were two transformations that did exactly what you would expect and two that didn't. What type do you think this is? Is it going to do what you expect or no? No. So what do you think would happen if I put in a big number for b? It's going to compress. Okay, if you put in a big number for b, okay, like let's say 5. So I'll just take get rid of those. Here's sine x, and here's sine 5x. Okay, sine 5x is going to repeat 5 times faster. So for every 1 period you're getting for the sine function, you're getting 5 periods of the sine 5x function. Okay? It's kind of hard to see, but I could show you it by going like this. 0 to 2 pi. And let me zoom in a little bit. Let's go -3 to 3. So now you're going to see exactly 1 period of sine. And you should see 5 periods of the red one. Okay, so you've got, that's 1, 2, 3, 4, 5. So it's repeating 5 times as fast because of the 5. We're only going to look at examples where b is greater than 0. If b were less than 0, you could do a reflection, but this time it wouldn't be over the x-axis, it would be over the y-axis. So period change is going to stretch or compress your graph along the x-axis. Okay, so looking at it kind of in a more interactive way, right, it does something like this. Okay, that's compressing, and that would be stretching. Okay, if you plug in a number bigger than 1, that's when you get compression. The bigger the number, the more compression you get. And if you plug in a number less than 1, that's when your graph will stretch. But remember, it'll be less than 1, but it's still going to be more than 0. So numbers between 0 and 1. Okay, so the effect of that is the frequency we would hear a sound at. Okay, so there are limits to what we can hear just because of the way our ears are designed. We can only hear up to certain frequencies. Does anybody know the upper limit? How many highest frequency humans can hear? We can't quite hear to 50. There are some animals or creatures that can. I think bats can hear really high. They can hear into the 6 figures. I can't play a sound that high, and even if I could, you wouldn't know. So, but yeah, we can't quite hear to 50. It's a little lower than that.
Great.
But it is in the 5 figures. It's closer to that. It's about 20,000. Okay, so 20,000 hertz is about as high pitch as we can hear. And I'm going to guess most people in this room can't hear that. We'll try it after. Let's see. So here's a sound that's a little over 1,700 hertz. Just turn it up a little so we can hear it. So everybody heard that? Okay, good. So you have the hearing equivalent of a fish right now. So fish have a really awful range of hearing. So if we go a little higher, up around 5,000 hertz. So it's getting higher pitch, but in terms of like frequencies of sounds, like 5,000 hertz is really very low. Okay, now we're up around 10 kilohertz, or 10,000, a little over 10.5 kilohertz. So it's getting higher pitch. I would say most people can hear that. Even when you get older, people can usually still hear that sound. Anybody that couldn't hear that one? No? Heard that? Okay, so now up around 13 kilohertz. We're getting into some sounds that some people might not be able to hear as well, but still, I can still hear that pretty clearly. Up around almost 17 kilohertz, I can't hear that. So I've lost that frequency now. And you will too someday.
I heard it.
Anybody else that didn't hear it? Yeah, it's 16,000. I didn't, 16.7, I didn't hear it. And then 19, I'm guessing there's some more people that probably lost that one.
Can anyone hear that?
You could start.
I heard that one, and I heard a lot.
Yeah, so that's about as high as we can go. Sometimes I think a sound around this frequency, I kind of hear it, from the older TVs. Anybody know what I mean? Like if a TV's on, you just can kind of hear like that. Maybe it's a little lower pitch than that,
I
but
can sort of hear that.
yeah.
But that's exactly when you just said you couldn't.
I don't know, I don't think so.
No, the last one.
No,
So that's kind of going towards the higher end. Okay, and then towards the lower end.
Mr. Hager's boy, Josh.
This is 50 hertz,
Wow, that's really.
which,
That just sounds like a.
It just sounded like a.
I don't
yeah, that pop at the beginning, that's
Oh,
not
I
supposed
think
to
that's
happen.
static.
Yeah.
I don't hear it.
It's hard to hear it because that speaker's not it's not a subwoofer, so it's not designed to make a frequency that low.
That's what.
That I'm just barely hearing now. And as you start to get a little higher, you'll definitely, now you can hear it.
Did you hear that one, Cliff?
So different frequency sound waves, they travel better than others. For example, this, if I were to play this frequency at like right where it is right now, even down a little bit, that would be an extremely loud sound. Well, if I find the right spot, it sounds louder. Like to me, that sounded louder, but it didn't change the volume. It's just because that frequency is a frequency people can hear better. Versus if I go very, very high pitch, now it's higher pitch, but the volume really didn't change. But people in the hallway probably wouldn't hear it.
Go to the max.
Okay, the max again.
No,
Yeah, Ron.
Cover your ears if you don't like the high pitched sound.
Ron.
Turn it down.
I don't hear anything.
Yeah, I don't hear it.
Wait, go to like 18,000.
18,000?
Could go.
It's about 18,000.
I hear that.
Wait, play it again.
It's still playing.
Yeah, it's still playing.
I can
feel. I can't hear it.
I can hear that.
You kind of just feel it. Yeah, eventually as you get older, you just lose those frequencies. So I hear about up to 16,000, depending on if it's loud enough. If you played 16,000, like down here,
Don't
I don't
see
think anyone can hear it.
like at about 6, I can't hear it.
it.
I can barely.
But you could probably hear other sounds at 6.
Yep. That sounds cool.
So 6 is still very easy to hear, depending on the frequency. Higher pitch, you can't. So. All right, so since we're stretching and compressing it along the x-axis, okay, the period is no longer going to be 2 pi. Okay, it's either going to repeat shorter than that, maybe it'll repeat in pi or half pi or even faster, or it's going to be longer. Okay, maybe it'll take all the way to 4 pi or 6 pi to repeat. So in order to figure out how fast it's repeating, we have to find the new period of the function. And this is the formula for finding the period. Okay, it's 2 pi divided by b, whatever is in front of x. Okay, if b is 1, okay, like in the problems that we did before, we can pretend like there's a 1 right there. The period of that function would be 2 pi divided by 1. Okay, so it would just be 2 pi. That's the normal period. But in a function like this, the period is not 2 pi. So some other kinds of questions you can have on the test, very similar to the amplitude ones, You don't have to graph it. I just want you to look at this and tell me the period. Okay. So what would be the period of this one? So some people say 2, some people say pi. So 2 is just the denominator of the period. 2 pi always has to go in the top. So then we get a period of pi. So did that compress it or did that stretch it? It compressed it by twice as much. The normal period is 0 to 2 pi. Now the function is going to do its whole thing in a shorter interval, 0 to pi. Okay. How about cosine 1/3 x? It's 2 pi over 1/3. And what's 2 pi divided by 1/3? 6 pi. Yep. So this is a stretch. Now, instead of going to 2 pi before you repeat, you're going to have to go triple as far before it repeats. So that's a very stretched out kind of wave. Okay. Any questions on that? Okay. How about y equals sine pi x? Yeah, the period here is just going to be 2. And what's nice about a problem that has a pi in front of x is it's going to cancel out the pi, and your x-axis is going to be nice numbers. Like you could number your x-axis 0, 1, 2. You wouldn't need pi on your x-axis here. And we'll do an example of that. Okay, how about the period here? And let me change this. What is it? It's 2 pi over 3. There's some other things happening. There's an amplitude change and a vertical shift, but neither one of those has an effect on the period. They affect other things. Okay, so make sure you know the number to focus in on if I ask for period. What's the amplitude here? What would be the amplitude now? 2. Still 2. What would be the period now? Still 2 pi over 3. So you can change those other numbers, and it only affects one thing. All right, so we're doing a period change. So what values are going to stay the same? The y values. Okay, the y values are going to stay the same, which unfortunately that means the x's are going to change. So the x's are the ones that have pi in them. So we're going to have to do arithmetic with pi. And now, what do you think we're going to do to find the new x's? Yes, we're going to divide. Because remember, we do the opposite. So when we did a vertical stretch, we multiplied the y values by the vertical stretch. This time, we're going to divide the values by b. That's one way to think about it. Now, a lot of times it's going to be easier to think of it a different way rather than the way I have written there. Dividing by b is the same as multiplying by what? 1 over b. And that's going to be the way you want to think about it most of the time. Okay? So this is the same as multiplying by 1 over b. And the reason that's going to be helpful is because a lot of times if you do it this way I put in parentheses, you're not going to have to think of fractions over fractions. Even if you do it the original way I wrote, you're going to have to do this anyway. You're going to have to multiply by the reciprocal because you're going to be dividing fractions. Okay, so any questions on that idea? Instead of dividing by b, it's the same as multiplying by 1 over b. All right, so let's try a couple examples. So in this problem, it doesn't ask for the period, but if I did, well, what's the period of this? It's 4 pi. Yep, because it would be 2 pi divided by a half. which is the same as 2 pi times 2. So, okay, so the period is 4 pi. So technically, since the period is 4 pi, that tells me where I'm going to end. You don't have to do that first. Okay? But let's go through the method I showed you on the other page, and I'll show you. We are going to end up right at 4 pi for the last number. Okay, so we're going to take all our x values. I'm just going to move this. And what are we going to do to all of these x values? Right, you could divide them by a half, which is the same as doubling. Now you can probably see why we're going to get 4 pi for the last one. Okay, so my x values are going to be 0. What's pi divided by 2 times 2? Pi. Pi times 2? 3 pi over 2 times 2. And the last one, 4 pi. Okay, so we have a nice pattern. And if you get a nice pattern, that's probably an indication you're on the right track. 0, 1, 2, 3, 4, all with pi. Okay, and what about my y values for sine? Yep. Okay, here's my table. And now I'm going to label my x-axis using the values in that table because they are equally spaced. They are all pi units apart. Okay, pi radians. What would that be in degrees? How far apart are they? They're 180 degrees apart. Okay, so we have to go all the way to 720 degrees before this function is going to repeat. But depending on how I scale my axes, you're not going to notice a difference. Okay, so I'm going to scale them like this. Pi, 2 pi, 3 pi, 4 pi. All right, and this will be 1 and negative 1. So 0, 1, 0, negative 1, back to 0. That's it. That's my graph. The original graph, if I were to do that one, would look, as you will have to do that in the homework. Put the original in red. It's not letting me. I'm trying to not stretch it proportionally, and it's not going to let me do that. Let's see if I can do this. There we go. All right, so the original would look kind of like that. It's not perfect, but it should have the same heights, but it would go from 0 to 2 pi. Okay, and the black one is the new one. Okay, so it's stretched out. Any questions on that? All right, so try cosine 2x. So take a second, see if you can figure out all the x values. Okay, so you're going to take all of these x's here and divide them by 2, which is the same as multiplying them by a half. So 0, pi over 4, pi over 2, 3 pi over 4, and pi. And you might look at those numbers and be like, there's no pattern there. But if you wrote everything with a denominator of 4, you would see the pattern. It's 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. But what we have is reduced. Okay, so fill in your x's. I would prefer that you do reduce it. 3 pi over 4 and pi. Okay, so make sure you set up your labels. If you forget those, you'll lose a point on the graph part. Okay. 1, 0, negative 1, 0, back to 1. Probably would have been a better idea to put the label above on this one, but That's fine. Or put the labels further down. That's fine too. Any questions on cosine 2x? All right, so let's look at the last one, and something nice is going to happen here because of the number that's in front of x. Okay. What's in front of x here that's going to make my x values turn out very nice? Yep.
Here's the pi that will cancel.
Yeah, so what's going to happen is all pi's are going to cancel. What would I do to all my x values here? Multiply by 3 over pi. You do the opposite. Okay, you're multiplying by the reciprocal. Okay, and I just said that all pi's are going to cancel. So what's my next x value? 3 over 2. Yep. Or we could write 1.5 if you want to see the pattern. My next one? 3. And basically, whatever the gap is between the first one and the second one, it has to be that gap the same. So the next one should be, and it is, 6/4. And the last one should be another 1.5. And 2 times 3 is 6. And then you just graph from there. Okay, so anytime you got a pi in front of x, it makes those values turn out very nice. Questions on that one? All right, so the homework, tonight it'll be the same deal as last night, worksheet. Okay, on those, it'll be about 8 questions. Test again will be on Thursday as a take-home. And I will be after school on Thursday for extra help. Yes?
You go